Hello everyone, I am Daniel Navarro. I come from IPCIT in San Luis Potosí, Mexico, and I am presenting this research work named Magnetocaloric Effect in Spark Plasma Sintered Melt-spun Ribbons of Nickel Manganese Tin Metamagnetic Alloys. As you can see from the abstract and introductory comments, this work is about the use of the magnetocaloric effect as an environmentally friendly alternative of replacing the current conventional refrigeration technology and the search for an efficient manufacturing process of the magnetocaloric materials. According to the last mentioned, spark plasma sintering appears to be a good alternative to fabricate those materials. SPS technique consists on the simultaneous application of an electric current and an unidirectional stress. So that's why we are assessing structural, microstructural, and magnetocaloric properties of alloy ribbons and its SPS sintered specimen. For this study, we started from melt-spun ribbons with a nominal composition nickel 50, manganese 37, tin 13, in order to process them by means of SPS. For the characterization, several analyses were performed to the precursor ribbons and they as sintered sample. The techniques are listed on this poster. In Table 1, we present the characteristic transition temperatures of both samples. This way is a little bit easier to compare the results that I'm about to explain. First, figure 1a presents typical microstructure of the produced polycrystalline ribbons at the cross-section with an average thickness of 33 micrometers. The room temperature X-ray powder diffraction in figure 1b shows that ribbons are constituted by a mixture of cubic austenitic and orthorhombic martensitic phases, which matches with the reporter for same alloy. The differential scanning calorimetry curves are plotted in figure 1c, whereas the characteristic temperatures of the transition are listed in table 1. Then, the thermal dependence of magnetization plot in figure 1d shows both the magnetostructural transition from ferromagnetic martensite and austenite phases, followed by the ferromagnetic transition of austenite that appears at Curie temperature of 313 Kelvin. The former shifts to lower temperatures when magnetic field increases to 5 Tesla. Afterwards, ribbons were cut and stacked into a 10 millimeters in diameter graphite die. The sintering was carried out under a pressure perpendicular to ribbon surface of 30 megapascals. Figure 2a shows the time evolution of temperature and vertical displacement along the process. From 771 to 1173 Kelvin, a continuous contraction appears during 200 seconds, indicating the occurrence of sintering. Then, current stopped since the highest consolidation was achieved. So, the micrograph in figure 2b clearly shows the interface between adjacent ribbons whose thickness is consistent with the initial one. Figure 2c shows the corresponding diffraction pattern where martensite and austenite peaks can be observed in agreement to DSC curves. The temperatures of the transition slightly shift to a higher temperature in comparison with the precursors. Figure 3a and b show the sets of isothermal magnetization curves up to 5 Tesla for the precursor ribbons and a sintered sample across the phase transition. Figure 3C and D show the entropy change curves obtained from the numerical integration of the Maxwell relation. The entropy change max value is located around 314 Kelvin. A sintered SPS sample virtually duplicates the value achieved for precursor ribbons. At 5 Tesla, spun ribbons display a maximum entropy change of 5.2 joule by kilogram Kelvin against 10.1 for the sintered sample. The entropy change increase matches with a structural rearrangement due to the SPS process serves as a thermal treatment for the ribbons. Therefore, we can conclude that the followed manufacturing method combines the advantages, characteristics of the precursor ribbons with the practicality of their consolidation into a highly dense piece as required for applications. So thank you for your attention. Feel free to send me a message if you have any questions.